Think about how you turn on a light. The switch is either up or it's down. The light is either on or it's off. Every piece of technology you use today, phone, tablet, laptop, operates on that exact same logic. We call it binary. Under the hood, these devices only understand absolute certainty, yes or no, a 1 or a 0. Look at this control panel from a vintage IBM mainframe. For decades, our digital world has been built around these rigid, manual states. We designed machines to process perfect black and white data because that is what silicon handles best. But the world we actually live in isn't black and white. It is messy. It is full of risks, shifting chances, and a million different maybes. Standard computers struggle to understand a maybe because they are forced to pick a side before they can even start the calculation. When we try to squeeze a complex, unpredictable world through a simple light switch brain, we run into a massive wall. Problems like predicting the weather or navigating a busy city require a machine that can hold multiple possibilities at the exact same time. This diagram compares our old light switch to a completely different approach. On the left, a standard computer bit, stuck like a flat disk. On the right is a qubit. Think of this as a spinning coin, a blur of both possibilities at once. Here, the dial is pointing straight up, perfectly balanced between two outcomes. This represents the moment the coin is spinning hardest, holding a maybe that is exactly halfway between a yes and a no. Look at this massive gold-plated laboratory structure. To build a physical machine that can hold a coin in that spinning state, engineers have to isolate it from the rest of the universe. They use giant cooling systems to make the hardware colder than outer space, just to keep that maybe from falling over. As long as this technology requires a massive freezing chamber, it stays locked in research labs. To bring this power to regular people, we have to find a way to let the coin spin on the standard laptops we already own. This graphic shows a different way forward. Instead of giant refrigerators, we use a clever map. We take the swirling chances of the real world and translate them into a structured grid that a normal computer can read. This 9-square grid is the foundation of that map. It works a lot like a high-tech tic-tac-toe board, and it's the primary interface for a system called Qxbin. Look at the 4 corners of this board. These outer squares act like solid fence posts. We lock our basic starting facts into these corners to create a rigid frame around the space in the middle. Now look at the edges connecting those corners. These are mixing zones. When the facts from the corners bleed into these edges, they overlap and create a blurred middle ground. This is where the computer finally learns how to hold a maybe. Follow the arrows pointing inward. All of that overlapping, uncertain information from the edges gets routed directly into this circular gate at the center. This hub handles the spinning of the data and gives us a final answer. By organizing information this way, we don't need a super-cooled laboratory. The grid acts as a trap, holding a maybe in place using nothing but clever geometry. When you turn this matrix on, those static ones and zeros wake up. The boring, rigid code is converted into a continuous, active flow. This diagram shows how that flow organizes itself over time. From the random-looking dots on the left, the system tracks the path of the data until it forms the distinct circular patterns you see on the right. Look at the plus and minus signs on this grid. Instead of picking one side and discarding the rest, the system maps those complex properties into positive and negative degrees. It turns the physics of maybe into a language standard computer chips can actually process. We've used math to do the work of a massive refrigerator, letting us simulate these complex states on the hardware we already use every day. Here is that math running right now on a standard laptop screen. Calculations that used to be trapped in expensive research labs can now be visualized and explored by anyone with a computer. But we can go even further. Imagine a physical object on your desk, a sphere covered in small pins. As the computer explores different possibilities, those pins push back against your hand. You can literally feel the maybe as a physical texture. Feeling the answer makes a complex guess feel as intuitive as playing with a well-crafted tool. You don't have to study an equation to understand where the momentum is heading. Your hand just knows. We've moved from just watching math happen on a screen to physically interacting with it, turning abstract chances into a sensory experience. For a long time, we were limited by computers that had to be certain about everything. Now, we are starting to add nuance to the way our machines think. Qxbin makes this type of intelligence available to every screen and every device. It turns your existing hardware into a machine that can handle the uncertainty of the real world. The coin is spinning, the matrix is alive, and we can finally explore these states on our own terms. The same simple shapes we use to play a game of tic-tac-toe have become the map that teaches our computers how to be faster, smarter, and a little more human.